Today we're going to talk about forced vibrations. This will be the situation where we have a system that models mechanical vibrations where the force is going to be minus k times u. Here u is our position function, and then we'll have a damping force minus gamma times u prime, but we'll also have some external force. Here that's the term F naught cosine omega t. And of course the force is mass times acceleration, and when we put everything in standard form, we get this differential equation, which is a second order linear constant coefficient, but now not non-homogeneous differential equation. Mu double prime plus gamma times u prime plus k times u equals this external force. Now, the external force can be all sorts of different things. I'm going to model an external force here, which is F naught, just some constant amplitude here, times cosine omega t. So the external force that's being applied is some sort of periodic force, like a cosine wave, with amplitude F naught. Omega would be the angular frequency here for the external force. Now, how do we solve this second order linear constant coefficient non-homogeneous differential equation? First, we solve the homogeneous equation, and we have a fundamental set of two solutions, u1 and u2. I'm not really going to care about those solutions too much. You know how to find them, and it depends on how big gamma is in relation to m and k, whether it's an underdamped and overdamped or a critically damped system. But here's the neat thing about this. Whatever the solution was, in all of those cases, these solutions, u1 of t and u2 of t, both involved exponential functions, things like e to the minus lambda t. In the underdamped situation, you had cosine and sine functions, so that there was some oscillation that was being damped like this. But actually, it was like e to the minus lambda over 2m times t. This was a negative number, so that as t goes to infinity, this goes to 0, and both of these solutions, u1 of t and u2 of t, die down very quickly. These are what we call transient solutions, and our solution to the homogeneous equation in any damped system will be a transient solution. This term here, the a cosine omega t plus b sine omega t, is what we would use, say, using the method of undetermined coefficients in order to find a particular solution to this differential equation. And you'll see that as t goes to infinity, these oscillations persist. These are our steady state solutions. So as for large values of t, the transient solutions become irrelevant, and what's important is what the steady state solution looks like. Well, how are we going to solve for the steady state solution? Well, essentially it's exactly what we've done before, just call this thing the steady state solution, capital U of t. Let me write that here, capital U of t. Our steady state solution was a cosine omega t plus b sine omega t. We've already seen that you can combine the cosine omega t and the sine omega t with amplitudes a and b into a single function that should be u of little t. I don't know why that's a capital T there. U of t is some amplitude r times cosine of omega t minus delta, where delta here is the phase shift. Now, if we take the differential equation, I'm going to go back to the previous slide here. We use the method of undetermined coefficients. We find, u of t. We find u double prime, u prime, and u, and plug those in here and solve for a and b. And then we use those a and b and solve for r. Remember here, the r squared is just a squared plus b squared. It's a whole bunch of algebra. It's a fun exercise if you have a big sheet of paper or several sheets of paper and you want to compute what this amplitude r ends up being. And here are the formulas that you get in the very end. This amplitude r for the steady state solution is just F naught, the original, that's the amplitude of the forced the external force, divided by this quantity capital delta, where capital delta here is given by this expression. It's the square root of m squared times this omega squared minus omega naught squared minus omega squared, all squared, plus gamma squared omega squared. Here omega naught squared is k over m. In other words, omega is the square root of k over m. This is the frequency of the undamped system. So the undamped, unforced system would have a natural frequency of omega naught, this square root of k over m. Omega here is the frequency of the external force. Now, this is all just a whole bunch of algebra. Here I put in, and these are all in the book, I put in how you can find the delta, the phase shift. That's not going to be of great interest to us. What I'd like to ask is, what can we say about the amplitude of the resulting steady state solution? Once you've gone through all this, you have an external force that you're applying whose magnitude is F naught. The F naught here is the magnitude of that external force. What can you say about the amplitude of the resulting steady state oscillations? Well, the amplitude of those steady state oscillations will just be F naught, that magnitude of the external force, divided by this quantity delta. And we can say a few simple things. If omega, the frequency, remember, let me rewrite this here, the external force was F naught cosine omega t. Omega is that frequency of that applied external force. If omega is close to 0, you can see from this expression in delta, this part will go to 0, this part will go to 0. We'll have the square root of m squared omega naught squared squared, and if we put in what omega naught squared is, that easily simplifies to r is F naught over k. K here, of course, was the spring constant for our system. And so for a very low frequency external applied force, the amplitude of the resulting steady state solution is just F naught over k. If you have a very high frequency force, imagine, coming from, say, an oscillating electrical current or something like that with a very high frequency oscillation, this delta becomes very big, because as omega gets big, this gamma squared omega squared gets very big here under the square root, and of course this omega squared, this part also gets very big, and so delta gets big, F naught over delta goes to 0. For a very high frequency external force, the steady state solution has a very small amplitude oscillation. What's going to be very interesting is what can cause the amplitude of the resulting steady state oscillation to become big. In other words, when is R big? Of course, R will be bigger if the external force is larger, but for a given external force, we might ask what frequency of oscillation of this external force causes the amplitude of the resulting steady state solution to be largest. And of course, that's an easy question to answer, because you'll get R to be largest. What value of omega, this is the question, for what value of omega is R maximum? R will be maximum when this quantity delta is minimum. And how do you minimize delta? That's a very simple Calc 1 problem. And it involves here a lot of algebra, because that's a messy formula. But you find that the frequency, omega max squared, the square of this maximum frequency, is exactly omega naught squared minus gamma squared over 2m squared, which, if we factor out the omega squared, you can write that as omega naught squared times the quantity 1 minus gamma squared over 2mk. This will give you the frequency, omega max, at which R is maximized. Notice that gamma here is the damping constant. And if gamma is very small, then omega max will be very close to omega naught, very close to the natural vibrational frequency of the system. So if you have a damped vibrating system with very little damping, then when you apply an external force, this omega max, what we'll call, what essentially is our resonant frequency, the one that causes the amplitude of the steady state solution to be largest, well, will be a frequency that's very close to the natural frequency of your vibrating system. And once you know omega max, you can plug that in to this formula F naught over delta and find R max. This maximum amplitude is just F naught over gamma omega naught times the square root of 1 minus gamma squared over 4 mk. We can just write this as a nice approximation. That's using the fact that 1 over square root of 1 minus x is approximately, 1 plus x over 2. If you just write out the power series, this is just 1 minus x to the minus 1/2 power. If you write out the power series, this is actually for a binomial type function. You'll find that this is approximately x over 2. That's when this thing is small. So again, in the approximation when gamma is small, the maximum amplitude is approximately F naught over gamma omega naught times this quantity, which is just a little bit bigger than 1. Now again, I said this is an approximation when gamma is small. If gamma is small, you'll see that F naught over gamma times omega naught times this other factor, which is close to 1, can be very large. So even for moderately small amplitude external forces, if those external forces are oscillating with frequency omega max, which is close to omega naught, then you can get very large amplitude steady state solutions. The one example I would like you all to appreciate is the example of the Tacoma Narrows Bridge. Some of you have probably seen the video of the Tacoma Narrows Bridge before. You should probably take a look at it again. I put the address for that, but I also have the link on the video lectures page on Canvas. So watch that video. That's only a 5-minute video. And what are you going to see with that video? Well, you've got a bridge held up by towers here, and you have wind that's gushing past the bridge. And that wind causes, the bridge itself, the deck of the bridge kind of acts like a wing, and with the rushing wind, that causes the deck to be moved upwards and then downwards and up and down, and starts to vibrate up and down at a certain frequency. That's an external force with a certain frequency that's determined by the wind speed and the shape of the deck, and that's being applied to the system. Well, this system, if you just didn't have any wind at all, and you pulled the deck of the bridge up a little bit, it would oscillate and very quickly return to its normal flat position as the oscillations died down, as with any damped mechanical vibrating system. But with this external force of the wind applied, and the wind in the area around the Tacoma Narrows Bridge can blow at large velocities for hours and hours and hours at a time and cause this continuous vibrating external force. If the frequencies line up perfectly, as they did in this particular example, watch the video to see what happens, you have this steady state solution where the bridge starts to oscillate up and down, and because of other things to do with the mechanics of the way the bridge is built, you see part going up while other parts are going down, and it vibrates up and down. Well, you can guess what happens when this happens to a bridge, and you don't have to guess. You should watch the video, and you'll see what happens. It's not good. Watch it till the end. You get to see what happens in the end. It's only about 5 minutes. So what's the lesson from all this? The lesson is, when you're designing a bridge, you should take these formulas here into consideration. And what does it mean to take these formulas into consideration? You should understand what sort of forces are caused by the wind, in particular the frequency of any oscillations caused by these external forces, the wind and anything else that might cause an external force. And you better design the bridge so that omega naught let's see here. So that omega naught is very different from your omega. Here's your omega and your omega naught. You should make sure those are very different so that this delta isn't too small, so that the delta is pretty big and that the R stays small for any steady state solution caused. These are induced vibrations caused by the external force. In other words, you don't want the resonant frequency from the wind to match up with the natural frequency of vibration of the bridge, at least to be very close, according to this formula, because when that happens, R max can get very big. You also want to design a bridge so that this damping constant is pretty large. So when people design bridges, they do put in things that increase the damping in the bridge so that, again, you don't get out of control oscillations when there's an external, a vibrating or oscillating external force that's applied. Now, the mathematics of this is all, I'll say, relatively new, a couple hundred years old, but people didn't really appreciate that well enough in engineering until much more recently. You can see the Tacoma Narrows Bridge example was from the 1940s, I believe, or right around 1940. But the principle was kind of understood even way back to Roman times. There are stories that Roman legions, when they would march across a bridge, remember, bridge construction back in those days probably wasn't as good as it is nowadays. The Roman legions normally would march in step, 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 and have these cause these regular vibrations on any bridge they went across. And if their vibrations happened to match the natural vibrational frequency of the bridge, which they had no way of knowing in advance, that could cause a bridge collapse. So Roman legions were, the legend goes, told that they would kind of break step when they went across bridges, and going across bridges, it would be some sort of irregular motion so as not to cause any resonant steady state vibrations that would get out of control and cause a bridge to collapse while they were on it. That would be embarrassing.